You ever look at a massive video game world or maybe a banking app that runs millions of transactions and just wonder, how in the world is something that complex even built? Well, it might seem like magic, but it all starts with a few fundamental blueprints. And today, we're going to unlock them.
I mean, really think about it. How do you take millions of lines of code and organize them so they don't just collapse into a giant chaotic mess? How do you actually model real-world things like a customer or a bank account or, a dragon in a video game?
Well, the answer is this really powerful idea called object-oriented programming, or OOP for short. And the best way to think about it is to stop thinking like a coder for a second and start thinking like an architect. You design blueprints, in code we call them classes, for every single thing in your digital world, from a simple button on a screen to a user's entire profile.
All right, so here's the game plan. We're going to look at the core principles, the main pillars of this whole blueprint idea. We'll see how we can build on existing foundations, how to create protective shields for our code, and how to make it super flexible. Then we'll quickly touch on a few other essential power tools every Java developer has in their kit. So let's dive in.
Our first pillar is inheritance. And honestly, this is all about being smart and, well, a little bit lazy in a good way. It's about efficiency. Why would you ever draw a brand new blueprint from scratch if you can just copy an existing one and add the few new details you need? It's all about reusing work that's already been done.
So, it all starts with a simple base blueprint. Let's imagine we create a class called person. It's pretty general, right? A person has a couple of basic properties that lots of things share, a name and an age. This is our master blueprint.
Okay, now watch this. This is where it gets cool. A student is a person, right? Of course. So instead of starting all over again, we just tell our code that our student class extends person. That extends keyword is the magic here. It automatically gets the name and age from the person class, and we just add the one thing that's specific to a student, a roll number. Easy. And this is where the real power kicks in. A result is tied to a specific student, so the result class extends student. Now, think about what that means. It gets everything from student, which, as we just saw, gets everything from person. So our result class automatically inherits the whole chain, name, age, roll number, and we just have to add the final specific details, the marks. That is code reuse in action. Beautiful.
All right, next up, encapsulation. If inheritance is about being efficient, encapsulation is all about being safe. It's like giving each one of your little code objects its own protective shield. This lets them guard their own data and basically prevents anyone from putting them into some kind of weird, invalid, or just nonsensical state.
Let's take a look at an employee object. We need to set their salary. Now, with encapsulation, we don't just go in and change the salary variable directly. No. Instead, we call a public method, which acts like a gatekeeper. We'll call it setSalary. We pass in a valid number, like 30,000. The object takes the value, checks it, and updates itself. Everything's working perfectly. But, mistakes happen. What if someone tries to do something that makes no sense? What if they try to set the salary to a negative number? That shouldn't be possible in the real world, and our code needs to be smart enough to prevent it. So we try to call that same setSalary method, but this time with negative 5,000. And bam, there's our shield in action. The object just rejects the change. Why? Because inside that setSalary method, the gatekeeper, there was a rule. Hey, only accept a salary if it's greater than 0. By bundling the data, which is the salary, with the method that controls it, setSalary, we've encapsulated it. We've protected our entire program from having bad data.
Okay, let's get into the real magic. Abstraction and polymorphism. These are two big ideas that work together to make our code incredibly flexible and, frankly, just clean. Think of it like this. Abstraction is about hiding all the messy complexity, while polymorphism is what allows one single action to have many different outcomes.
First up, abstraction. We can create an abstract idea, like a shape, just the concept of a shape. We know that every single shape in existence has to have an area, right? So we can declare a method called calculateArea. But notice we don't say how to calculate it here. We're hiding the nitty-gritty details. The formula for a circle is totally different from a rectangle. But from this high level, all we need to know is that they both can calculate an area. That's it. And that idea leads us directly into polymorphism, which literally means many forms. Just look at this table. We've got 3 different bank classes here. They all inherited from some base bank class, and they all have a method with the exact same name, getRateOfInterest. But here's the thing. Each one implements that method differently, returning its own unique interest rate. Same name, totally different behaviors.
So, where does this many forms idea really shine? It's right here. We can create a variable of the general type, bank, but the actual real object we put inside it is a specific SBI object. See what we're doing? We're programming to the general idea, the abstract concept, not the specific little detail. So here's a quick question for you. The variable B1 is of type bank, but the object living inside it is an SBI object. When we call the getRateOfInterest method on B1, what's it going to give us? Which version of the method actually gets called here?
The answer is 8%, and this is a perfect demonstration of what we call runtime polymorphism. Even though our variable type was the generic bank, Java is smart. When the code actually runs, it looks inside and checks the actual object that's there. It saw an SBI object, so it called SBI-specific method. If the object inside had been ICICI, it would have returned 7%. That's the magic. One single method call can have many possible outcomes, depending on the object.
So those 4 pillars give us our core architecture. But a master builder needs more than just blueprints, right? You need some power tools. So let's quickly add 2 more essential tools to our kit for handling stuff happening all at once and for dealing with errors.
First up is multithreading. This is what lets your program basically do multiple things at the same time. You know when you're downloading a huge file but you can still scroll around on a web page? That's multithreading. Here, we've given the program 2 jobs that can run simultaneously. One thread prints all the odd numbers, and another one prints all the even numbers. This is what makes modern software feel so fast and responsive. And finally, exception handling. So, what happens when things go wrong? When a user types in their name where a number is expected? Without a safety net, your program just crashes. Well, exception handling is that safety net. You try the risky piece of code. If an error, an exception, occurs, a catch box swoops in, grabs it, and handles it gracefully, maybe by printing a helpful message, instead of bringing the whole program to a screeching halt. Okay, so we've covered the big architectural principles, and we've added a couple of power tools to our belt. Let's bring it all home and recap that core blueprint. This is it. This is the 4-part blueprint of modern software. Inheritance lets us avoid redoing work. Encapsulation builds those crucial protective shields around our data. Abstraction keeps our designs clean by hiding all the messy details. And polymorphism gives us the incredible flexibility to make one interface perform many different actions.
So I want to leave you with this final thought. The next time you open an app on your phone or you use a piece of software on your computer, try to look past the pixels on the screen. See if you can spot the invisible architecture. Can you imagine the objects, how they're inheriting from each other, and how they're protecting themselves with those little shields? Because now you know the blueprints they were all built from.